It is section 7.4, Kernel Principal Component Analysis, Kernel PCA. It is an extension of the PCA using kernel techniques for a nonlinear PCA. We'll begin with a recall for the standard linear PCA. The data matrix X is in n by d dimensions, and each row of the data matrix represents a data point, and each column gives a particular kind of feature, and the data matrix is standardized so that each column has zero mean. Now, the goal of the standard PCA is to find an orthogonal weight matrix such that the transformation produces score matrix. Once you are choosing truncated weight matrix, then the transformation is the truncated score matrix. And columns of Z represents the principal component of X. Now, earlier, we figured out that WK is the collection of normalized eigenvectors of X transpose X. Here, WJ, lambda J are eigenvalue pairs of X transpose X and normalized, and WK is the collection of the first K eigenvectors of X transpose X. Of course, here, corresponding eigenvalues are in decreasing order. And also, we recognize that the score matrix is scaled eigenvectors of XX transpose. And XX transpose has the eigenvalue lambda J, the same as for X transpose X, but eigenvectors are different. And once it's normalized, then ZK can be written in this way. The collection of eigenvectors now scaled by here square root of lambda. Then for every point vector X, it can be transformed to a k-dimensional row vector by this weight matrix. Once we are using singular value decomposition, so that if we get X as U sigma V transpose, then sigma with singular values on the diagonal in decreasing order, then we can see that here W and V are the same, but we are using here approximation notation. Now, when you try to get the eigenvectors, then this can be involving here negative of that V matrix, so that except -1 multiplication, they are the same. And also we can see easily that sigma j squared is same as lambda j, so that the truncated score matrix can be rewritten in this form. That's the recall. Okay, here now we begin the principal components, considering principal components of the kernel PCA. Here, C is the covariance matrix of X, and with here scaling factor 1 over n, but you don't have to put 1 over n. And the major part is X transpose X. Now, it can be written in this form. For each data point, here out product is made, and this rank 1 matrices are added and averaged. And for each component, the CJK, JK's value inside of the matrix, you can get in this way. That is basically J's column and case column of the data metric and in the product. Okay. Now, kernel PCA is a generalization of the PCA, and first the data set is transformed into a higher dimensional space, and as in kernel supported vector machine, we transform the data into a higher dimension. So P is larger than D. So this is now transformed data points and in higher dimension. Okay, then the corresponding covariance metric can be formed in this way: 1 over n times xx transpose, now phi xi and phi xi transpose. So in metric notation, we can write in this way. Now C is in P by P dimensions. So here we have to compute eigenvectors and eigenvalues, and now so that we may start with here solving this eigenvalue problem. And CV is a lambda V, and assume this is solved then with a decreasing order of eigenvalues. Here, now the VK, the truncated here weight metric, that is now VK is the collection of first K eigenvectors. Now they are normalized here. Then the score metric, the truncated score metric, can be made in this way. So the phi x, the now transformed data metric, and here the weight metric. So score metric can be gotten in this way. That is exactly an analog to 7.76. Here you can see here now. Okay, that one. Okay. Okay. However, now solving this problem is not simple, and because there's the expansion to a higher dimension, and if you are using some convenient the norm function, then P can be very large, or P can be infinity. So in this case, the computation of this, solving this problem is computationally expensive or impossible. So we have to consider something else. Here we have an alternative to the computation of a score metric. Now we'll begin with a claim. V is an eigenvector of C as in equation 7.84. Okay, that one. So assume V is an eigenvector. Then the eigenvector can be expressed as a linear combination of data points. Here alpha I, phi, xi, and I summation. So through the points, it's a linear combination of data points. V can be expressed in this way. Here a proof. If we start with this CV equal lambda V, then by using the definition, okay, that portion is C. Okay, here from here to there is C. Now this dot product, this product will make a scalar. To use that, here we start with a V is now divided by lambda, 1 over lambda n, and here this portion is a scalar, and so put it over there. So that if we define 1 over lambda n, the constant, and this portion as alpha I, then now V can be expressed as alpha I phi xi summation. Okay, so eigenvector of C covariance matrix can be written as here now in this form. So linear combination of data points. Okay, that means here now all eigenvectors V lie in the span of that data points. Now, so finding an eigenvector in that equation is equivalent to finding the coefficients alpha. So here, once we can find alpha, then that's the end. Okay, here we have how to find alpha. Now let's begin with the specific eigenvector and eigenvalue. So CVJ is now lambda j Vj. So J's eigenvector and eigenvalue. And assume lambda j is non-zero. Then here Vj can be written in this way. Now j is another subscript, and now L summation here, L is from 1 to n alpha Lj and phi xl. So in matrix vector notation, we can write here that is now the data metric, the transformed, expanded data metric transpose and alpha j. Okay. Here now using that expression, and CVJ lambda Vj can be written in this way. Now Vj is this portion. Okay, so that is now here this portion. Okay, here to there is now Vj, and that is now C and lambda j and Vj. Right? Now for this one, we pre-multiply phi x. This one, now phi of x, the data matrix is multiplied in left-hand side. Then we define, because that one has one phi x or phi in transpose, and this is a 3 matrix multiplication, so that by multiplying one more, it becomes 4 and it becomes 2. And if we define and this portion as k, so that's called similarity matrix. K is now defined in this way. Then left-hand side will be here k squared alpha j, and right-hand side, that one will be k alpha j. And by multiplying n over there, we can reach at here k squared alpha j and n lambda j with the constant, now k alpha j. Okay, k may not be invertible. However, we may eliminate the k, 1k. Then here, maybe this vector may be changed. However, only it affects the null space when here it can be written in this eigenvalue problem. If we define this portion as mu j, then now that becomes here eigenvalue problem. Now if we eliminate k, then here it is not the same. However, and for the components having positive eigenvalue is not affected. Only change can happen with null space, but later on we'll not use null space. So it's really okay mathematically. So we reach at that problem. That means that here alpha j is eigenvector of the similarity kernel metric. Okay. So here, by finding in alpha j as now the kernel metric and similarity metric, we can decide here, and along with the alpha j, we can decide the Vj, right? Okay. Now here, before going to the computational aspect of this kernel PCA, we need to consider here normalization condition. V is norm, the eigenvectors, Vj has norm 1. Now, if we are, now we start with that way, Vj is now the metric, and that is theta metric transpose and alpha j, then the norm of Vj is 1. However, now norm of alpha j, even though it will be computed here from that eigenvalue problem, now in this formula, alpha j doesn't have to have norm 1. In fact, norm of alpha j must be 1 over square root of mu j, the eigenvalue. The mu j is eigenvalue of the corresponding eigenvector alpha j. We can see it quite easily. And now Vj transpose Vj is 1. Now Vj is written in this way, so that we have here transpose and the vector. Then we can recheck that one. And that is now metric K. So K alpha j will be mu j alpha j. So that is same as mu j alpha j norm squared. So that must be 1. So that here alpha j norm must be 1 over square root of mu j. The reason we are considering this normalization condition is that later on, when you are trying to compute the eigenvector of K, then the output in the computation will be with a normalized eigenvector. So norm of eigenvector alpha j will be 1 in computation, so that once you try to use the alpha j, then now for that formula, you will have, again, adjust. You have to give some extra scaling factor. If that norm is 1, then you will have to scale appropriately so that Vj is computed correctly. Okay. Now here, one more thing here. Now K is in n by n dimensions, so that the number of points n can be smaller than p. Earlier, we considered the data expansion from D to P dimension, so that maybe this one is much larger than N. So that along with this alternative technique, and here the computation can be in less expensive. Okay. Now we'll continue in the second part. Thank you.